Exercise 5 of Chapter 9 is a direct follow-up from Exercise 4. So you'll need all the code and also the concepts from Exercise 4 to work through this exercise. So make sure you've already done that exercise. So the goal here is to take all the code from the previous exercise, put it into a for loop so that we can run it many, many times to compute the distance or the error of A times A inverse using these two different methods, and that error relative to the true identity matrix. Okay, so we're going to run it 100 iterations. So basically, we're running experiment or the exercise for 100 times, and each time we store the Euclidean distance, and then we're going to make a plot that looks like this. Now, what you see here is each dot corresponds to a random numbers matrix. So we ran through this code 100 times, so there's 100 of these dots. It may look like there's a lot less than 100, but these are, some relatively large distances. Most of the data values are clustered around here. So this is for the kind of traditional textbook method to invert matrices. This is for QR decomposition. Here we see for a 5 by 5 matrix, and here is for a 30 by 30 matrix. And the idea is that as the matrices grow in size, the QR decomposition really becomes more numerically stable. And this would also be the case for matrices that are more difficult to invert, for example, because they have a larger condition matrix. Okay, then there's some other things about the y-axis, which I'll talk about more when I show the code for this exercise. In terms of coding, there's not a whole lot that's new that you need to do for this exercise. You can see I've added some numbers here, some variables. So the number of experiments, here's a variable to collect all of the sum of squared errors. And then here inside this for loop, this is really just all the code from the previous exercise that I've put into this for loop. Most of the new code for this exercise is really just the visualization stuff. Okay, so let's run this first cell. And here we see this is the result for a 5 by 5 matrix. So it looks like there's one outlier matrix. So there's one matrix that was just harder to invert for whatever random reason. We don't store these matrices, so I don't have any way of going back to see what was wrong with this matrix. But I suspect that just randomly by chance, it probably had a relatively high condition number. And so, so the matrix is more spread out in some directions and more compressed in other directions. And so it was just a little bit numerically harder to evaluate. So that's for a 5 by 5 matrix. And now what we can try is setting this bigger. So let's say we'll make it a 30 by 30 matrix. So quite a bit bigger. And now we can see it also takes longer to compute. Here you see the results. And again, smaller numbers are better. And what you see is, so the bar, the gray bar here shows the average. You can see that the average error, the average of the inaccuracies, is a lot lower for QR decomposition than it is for our old school method. Still quite small. Maybe I'll plot the log of this. Let me see. But NumPy, when you have really small numbers that are positive, but greater than 0, but much less than 1, then it often is helpful to plot the log of those numbers. And that's basically because the logarithm will stretch out the really, really tiny numbers. So it just makes it visually a bit easier to see. So I ran that, and then I just had to take a moment to also see that I should make everywhere I compute the SSE to be the log here. So I just updated a few extra lines of code. Okay, so here you see the log. You can see these are now negative numbers because the log of a number less than 1 is negative. And okay, I don't know if this really helps the visualization or not, but you do see that maybe it is more clear now. You do see that all of the QR values, error values, are smaller than for the traditional method. Again, these are larger matrices, but they're still pretty easy to invert, numerically speaking, because random matrices just have very nice properties that make them suitable to complicated linear algebra operations and decompositions, including matrix inversion. Nonetheless, you see that on average, QR decomposition is more numerically stable than the old school method. Now, the other thing that I wanted to mention is that even though QR, there are more stable methods than what I presented in the previous chapter, you still get quite some errors for large matrices in particular. So, these errors are not zero here. So here the log of these errors is somewhere around minus 30. So keep that number in mind, minus 30. And now I'm going to set this back to be 5 by 5. So the log of the errors here were minus 30. And now you can see, okay, well, for QR, it's still around minus 30 to minus 35. It's actually a pretty significant difference considering this is log scaled. And here for this old school method, this also went down considerably. Remember before it was up here closer to 25. So that's a pretty significant drop in the errors, which means that even these stable algorithms start performing much worse for inverting relatively large matrices. And 30 by 30 is, that's not that big for an application. 30 by 30 matrix is still pretty small when it comes to real linear algebra applications in statistics and in machine learning.